The distinction between how data is stored within a system can be the difference between a functional application and a broken one. In Python, understanding whether a piece of data belongs to an individual object or to the entire group is a fundamental skill. Let's start on the left with instance variables. Think of this as personal data. It belongs to exactly one object and it's different for every object created. You can see in this diagram that we have three distinct objects and each one holds its own unique value like A, B, and C. Now let's look at the right side. Class variables. This represents shared data. This information belongs to the class itself rather than any single object, making it identical for every object associated with that class. Notice how the shared value of 100 cascades down so all objects share that exact same value. It is incredibly important to keep these straight. As you can see right in the middle, failing to distinguish between the two is one of the most frequent causes of bugs that survive all the way into professional production environments. To understand this physically, consider the environment of a large company. Every employee is issued their own personal laptop. This laptop is our instance variable. It belongs to that specific employee only. If the screen breaks on one laptop, no one else's laptop is affected because they all have their own separate hardware. In contrast, all these employees share a single company Wi-Fi password. This password is a class variable. It is exactly the same for everyone in the building. If the IT department decides to change the Wi-Fi password, that change doesn't just happen for one person. It changes for everyone at once. The core takeaway is that personal items are instance variables while shared items are class variables. Next, we will explore exactly where we write these specific variables in our code structure to make this happen. So where do we actually put these variables in our code? Let's look at the rules for where variables live. Class variables are defined directly under the class name and crucially, as we see highlighted here, they use no self prefix. On the other hand, instance variables are defined inside the special init method and they always use the self prefix. The basic decision rule is simple. If the data should be the same for all objects, you make it a class variable. If it needs to be different for each object, it's an instance variable. Let's see this in actual code down here on the left. Inside our class definition, right under the class name, we define our class variables like manufacturer and total cars made. Notice there is no self here. Then further down, inside the init method, we define our instance variables starting with the self prefix like self.model and self.color. Now let's walk through how this structure actually behaves over here on the right. At the top level, we have the class Tata car. The manufacturer and total cars made variables live here. Because they are at the top level, they are shared by all objects below them. Below the class, we instantiate individual objects. For example, car 1 is a Nexon with its own red color and car 2 is a Harrier with its own white color. These are their personal instance variables. The bottom section shows us why this sharing structure matters. If you change a class variable, that single change updates all objects instantly. But if you change an instance variable, it is unique to that specific object, so only one car is affected. The fundamental takeaway is that class variables act as master settings shared globally by the group, while instance variables act as private data unique to each object's identity. With these definitions clear, we can see how applying this concept to a massive operation creates incredible efficiency. In the context of a manufacturer like Tata Motors, the company builds thousands of vehicles. Every single car shares the same manufacturer name, Tata Motors. By setting this as a class variable, the system becomes highly efficient. If the company rebrands to Tata Motors Ltd, updating that one class variable instantly reflects the change across every car object in the system.
There is no need to manually update 10,000 individual records. However, each car must maintain its own identity. The model, the specific color, and the unique engine number are kept as instance variables because they differ from one car to the next. Netflix applies this same logic to manage millions of global users. They use class variables for platform-wide settings that apply to everyone, such as the platform name, which is Netflix, or the content rating system. Meanwhile, your personal watch history, your specific subscription plan, and your preferred language are instance variables. This separation is critical for stability. It allows Netflix to update the entire rating system for every user globally by changing one class variable without risking or needing to touch the personal data of individual subscribers. Now, consider the logic of the Tata car code on the left. The class begins by defining manufacturer and total cars made. These are shared. Inside the init function, we see self.model, self.color, and self.engine number. These are unique to each car created. The code uses a specific mathematical operation. Tata car dot total cars made plus equals 1. This line means that every time a new car object is born or initialized, the shared counter in the class goes up by 1. Because this variable lives in the class, it keeps a running total of all cars, regardless of which specific object triggered the increment. When we create car 1, car 2, and car 3, the total cars made increments up to 3. If we then run an update to the class variable setting the manufacturer to Tata Motors Ltd and check car 1 and car 2, both will show the new name. They are looking at the exact same shared resource. But if we change an instance variable like setting car1.color to black, car 2's color remains white. The instance variable change is completely isolated to that specific object. Always remember, class variables manage shared state, while instance variables manage unique identities. We can further verify these concepts by looking at how a logistics company might manage a fleet of trucks.
To verify these concepts in action, let's consider a truck class for a logistics company. When designing this, we have to decide what data is shared and what is unique. Class variables might include the company name or the maximum speed limit for the entire fleet, since these apply to every truck equally. However, instance variables must be unique per vehicle, such as the license plate, the current load weight, and the driver's name. What happens if we make a mistake here? Let's look at this middle section. If you accidentally define a unique item like a license plate as a class variable, you create a major production bug. Because it's shared, every single truck in your system would end up displaying the exact same license plate number. Specifically, whatever the number was for the last truck created. This directly causes data corruption. Another trap to avoid is trying to change a class variable by using an object instance. For example, if you write car1.manufacturer equals something else, you might think you are updating the shared variable for the whole fleet. But in many systems, this actually just creates a new personal instance variable for car1. This new variable shadows or hides the class variable for that specific car, while the original class variable remains unchanged for everyone else. This can cause confusing, hard-to-track logic errors in your code. To really cement this knowledge, let's look at a practice problem building a bank account class. First, we define our data. We have two shared class variables, the bank name set to State Bank of India and an interest rate set to 0.05 representing 5%. The personal instance variables for each account will be the account number, the owner's name, and their specific balance. Next, you will implement a method called apply interest. Mathematically, this method takes the current balance and increases it by our shared interest rate. For example, if an account's balance is 1000, the calculation is 1000 plus the quantity of 1000 times 0.05, resulting in a new balance of 1050. Let's watch this scale. We create 3 different accounts with varying balances. When we run the apply interest method at the 5% rate, all of their balances successfully update. Now, here is the magic of class variables. Imagine a central bank change occurs.
We can update the rate for everyone by just changing the class variable. Bank account.interest rate equals 0.07. Now when you run the apply interest method again, that new 7% rate is automatically applied to all accounts. You didn't have to go in and modify a single individual account object. This is the efficiency of global control. The ultimate payoff of this concept is that you now know how to structure your data for massive scale. You can confidently separate individual unique data from shared collective data. Because of this, you can build systems where massive global changes are executed in a single line of code, all while perfectly maintaining the integrity and consistency of the unique personal data for every object you create.